So the final thing that we need to look at today is organic reactions. And so this is because understanding organic reactions and reaction pathways is not only going to enable us to understand what's happening in certain reactions and what sort of organic reactions are shaping the world around us, but also allows us to narrow down what organic molecules are through a series of different tests. So for example, carboxylic acids, they're obviously an acid, they're going to have a pH above 7. So if we tested the pH of an unknown solution and the value was above 7, we know a carboxylic acid is going to have a pH below 7 because it's acidic. So if we test the pH and the pH is above 7, we know that's basic, it's not going to be a carboxylic acid. So before we look at the organic reactions though, we need to have an understanding of saturated and unsaturated compounds. So saturated compounds are going to be compounds that contain only single bonds. So this basically means that all carbons have 4 single bonds. The maximum number of hydrogens possible for the molecule are possible due to there being only single bonds. So the molecule is entirely saturated with hydrogens. Whereas unsaturated compounds will contain at least one double or one triple bond. And so they're not fully saturated with hydrogens. They can be either monounsaturated compounds, so meaning they have one double bond, or polyunsaturated compounds, which means they've either got multiple double bonds or triple bonds. And so by definition, an alkane is going to be saturated because it's got all single bonds along the backbone of the carbon molecule, and alkenes and alkynes are always going to be unsaturated molecules because they've got at least one double bond or one triple bond along the main carbon chain. We also need to look at primary, secondary, and tertiary carbons. And so when we look at these, we're always using the convention of 1 degree, 2 degree, and 3 degree to mean primary, secondary, and tertiary. So those are just like our shortened names for representing what primary, secondary, and tertiary are. And so a primary carbon atom is going to be the carbon atom which is connected to one other carbon atom. Or for example, in methane, no other carbon atoms. A secondary carbon atom is going to be connected to 2 other carbon atoms. And then a tertiary carbon atom is going to be connected to 3 carbon atoms. And so these are used to describe the location of functional groups. So as we've spoken about before, with our alcohols we have primary, secondary, tertiary, and with our amines we've got primary, secondary, tertiary. We can also do this with haloalkanes as well to describe the location of the halogen groups. So this concept of primary, secondary, and tertiary is very useful in describing our functional group locations. So now going on to our organic reactions which we need to know. So the first one which we're going to look at is a substitution reaction, and so it's a substitution of alkanes in order to make haloalkanes. So what alkanes are is they are a very unreactive molecule, and so this is because they have high stability in their hydrogen to carbon bonds, so in their hydrocarbon chain. And so we've seen that before in that an alkane is fully single bonded. And so this means that they're very unreactive. They're not going to react very easily, so hence they need what's known as a catalyst. And so their catalyst is going to be UV light. So this reaction will only occur in the presence of UV light, whether that being sunlight or specifically artificially created UV light. And when they are in the presence of UV light, they can react with halogen gases to form what's known as our haloalkanes. So for example, if we started off with an ethane molecule and we were to put it in the presence of UV light and chlorine gas, so Cl2, we could form a chloroethane molecule. And so when we form the chloroethane molecule, we're switching out one of the hydrogens for a chlorine atom. And so when we switch out one of the hydrogens for a chlorine atom, we then are left over with one of the chlorine atoms from the Cl2 and the hydrogen atom which has been taken out of ethane, leaving us with chloroethane and HCl. So our main product which we would produce would be chloroethane, and then our byproduct which we would produce would be HCl, or hydrochloric acid. The next one we can look at is the substitution of haloalkanes to make alcohols. So there's 3 types of these ones which we can look at, and in each case the halogen on the haloalkane is replaced by another atom or a group of atoms. So we've got the substitution of haloalkanes with hydroxide, and in this case a primary haloalkane will form a primary alcohol, a secondary haloalkane will form a secondary alcohol, and a tertiary haloalkane will form a tertiary alcohol. We also have a substitution of haloalkanes with ammonia in order to make amines. So for example, if we take something like chloroethane and we combine this with ammonia, so NH3, we can replace the chloro group with the amine group, so with the NH2 from the NH3, leaving us with ethylamine, and then we'd have a leftover hydrogen from the NH3 because we've only put in NH2 into the molecule, and we'd have the leftover chlorine from the original chloroethane molecule. So our main product would be ethylamine, and then we'd have a byproduct of HCl, being the leftover hydrogen from the NH3 and the chlorine from the chloroethane. The next one we want to look at is the substitution of haloalkanes to make nitriles, and so this is done by substituting haloalkanes with cyanide. So for example, again, starting off with chloroethane, if we are to use KCN, which is potassium cyanide, in ethanol, so the potassium cyanide must be in ethanol in order for this reaction to occur. We can then combine that with the chloroethane, and this will produce ethane nitrile. So what happens here is that the chlorine group is lost along with these 2 hydrogens here, and it's replaced with this triple bonded nitrogen group here, and then we end up with a KCl, potassium chloride, as a byproduct to this reaction. So our main product would be the ethane nitrile, and then our byproduct would be the leftover halogen from here, or whichever group this is from here, the potassium, our halogen from here, the chlorine, along with our potassium, which is left over from here. So the KCl being potassium chloride being our byproduct to the reaction. The next one we can look at is addition reactions, and so addition reactions of alkenes to make haloalkanes, and so this is done by producing haloalkanes by combining alkenes with halogens. So for example, if we start off with a molecule like ethene, we can do a dihalogenation, and so, or just known as a halogenation. And so this is where we take our ethene molecule, for example, so it's got a double bond in the middle, and what we do is we break this double bond, and then in order to ensure that the stable octet is attained, we can substitute in these bromine groups to then make this a dibromoethane. So this is incorrectly labeled here where it says bromoethane. That should say dibromoethane to specifically show that we have 2 halogen groups here, 2 of these bromine molecules. Our next one down is where we're adding HBr. So instead of adding Br2, we're adding HBr, and so HBr is going to mean that we're doing a hydrohalogenation. So it's hydrogen and a halogen being substituted into the ethene molecule. And so what's happening here is we break the double bond, and so once we break the double bond, we need to complete the stable octet, and so we do this by adding in the hydrogen and the bromine, causing this to form bromoethane. And so when we look at these addition reactions, we need to consider something called Markovnikov's rule. And so what Markovnikov's rule says is that the hydrogen atom is going to be more likely to bind to the carbon which has more hydrogens bound to it already, and the halogen is going to be more likely to bind to the carbon which has fewer hydrogens already bound to it. So for example, when we look at something like this molecule here where we've got a propene molecule. If we add HCl to a propene molecule, we can form both 1-chloropropane and 2-chloropropane. And so both of these will be formed. However, we'll have a main product, so our major product, and we'll have a minor product. So there'll be substantially more of one of these possibilities produced than the other. And so there'll be substantially more 2-chloropropane produced as opposed to 1-chloropropane. And so this is because 2-chloropropane, on the second carbon along on the molecule, there's only one hydrogen bonded to it, whereas on the third carbon along, or the first carbon along on the molecule, there's two hydrogens bonded to the carbon. And so Markovnikov's rule is saying that hydrogen is going to bond to the carbon which already has more hydrogens bound to it, so it's going to bond to the CH2 part of the molecule as opposed to the CH part of the molecule, resulting in 2-chloropropane as opposed to 1-chloropropane. So we'll end up in this reaction with producing mostly 2-chloropropane. However, there will be a very small amount of 1-chloropropane produced. The next one we can look at is another addition reaction, where we've got addition of alkenes to make alcohols. And so in this particular addition reaction, we add water to alkenes in order to produce alcohols. But what we can notice with this here is that we can't just add water as it is, because if we're adding ethene to a water molecule, ethene is fairly unreactive with water as well, because water is fairly unreactive. So we need an acid catalyst. So we're using H3PO4, just because this is a fairly unreactive acid, but it can be used as a catalyst. And so when we add ethene to H2O under an acid catalyst, we can produce ethanol. And so as we can see here, we don't need to apply Markovnikov's rule to this particular circumstance, being ethene, because each carbon atom has the same number of hydrogens bonded to it. However, if we had a larger molecule, we would need to apply Markovnikov's rule to this particular circumstance to show which particular one would be the major product. So whether the hydrogen would be bonding to which particular carbon and which one the hydroxyl group would be bonding to. And so what we've done in this particular reaction is, like the halogenation ones, we've broken this double bond, and then we've formed a single bond here, and then added the hydrogen and the oxygen and the hydrogen from the water in order to make this ethanol molecule. The next one we can look at is an addition reaction of alkenes to form polyalkenes. And so this is known as a polymerization reaction. We're producing polymers. And so this is talked about a lot further into Unit 4, so I won't delve into this too much, but I will just briefly give an overview of what this is. So basically, if you combine alkenes with a catalyst such as TiCl3, you can form what's known as a polyalkene. So for example, here we're looking at a propene molecule. If we combine multiple propene molecules under this catalyst, we can form a long chain of alkene molecules in which they have these methyl groups placed incrementally along a very long chain. And so these are used in very many industrial applications to create plastics, fabrics, all those types of things, because they can create very long continuous molecules. The next addition reaction we want to look at is an addition reaction of alkenes to make alkanes. So this is adding H2 under a platinum catalyst or a nickel catalyst, just any inert metal, in order to create an alkane. So we've got ethene, and because ethene would be unreactive, we've obviously got that catalyst, and when we add H2, we're breaking this double bond and adding these two hydrogens in order to make this into an ethane molecule as opposed to an ethene molecule, and to reattain that stable octet. The next reaction we can look at is an esterification reaction. So an esterification reaction is a reaction in which we can make esters through a reaction between alcohols and carboxylic acids. So the general rule for this is that we combine an alcohol plus a carboxylic acid, and so the alcohol part will form the alkyl group of the name, and the carboxylic acid will form the alkanoate part of the name. So for example, if we were to combine ethanol and methanoic acid, we would need to use a concentrated H2SO4 catalyst, so a concentrated acid catalyst, in order for this reaction to occur, and this would then produce an ester, being ethyl methanoate. So the ethanol part becoming the ethanol part becoming the alkyl group, the branched off chain, and then the methyl part becoming the methanoate group on the end. And then this reaction, obviously we'd be breaking the bond here and breaking a bond here, so we'd also produce water in this particular reaction as a byproduct. And so this reaction can be reversed to go back the other way, and so we can add water and an ester to make a carboxylic acid and an alcohol. So this is a reversible reaction. Our next reaction we want to look at is making amides. So in order to make amides, we can combine carboxylic acids and either an amine or ammonia under high heat as a catalyst in order to make an amide. So for example, when we combine the carboxylic acid and either the amine or the ammonia, we're breaking the bond where the OH, the hydroxyl section is on the carboxylic acid, and we're removing that, and then we're joining that to where the hydrogen was on on either the amine or the ammonia. And so this performs the amide, with the part with the double bonded oxygen being the carboxylic acid section, and the part with the ammonia and the nitrogen being either the original amine molecule or the ammonia section. And as we can see, we've removed a hydrogen from the amine or the ammonia molecule, and we've removed the hydroxyl group from the carboxylic acid molecule. And so that leaves us with a byproduct of water in this reaction. And so this reaction is also reversible in the forward direction. It's a condensation reaction. We can reverse the reaction back again as a hydrolysis reaction, so we can add water and an amide in order to form either ammonia or an amine and a carboxylic acid. We've also got a reduction reaction to make amines, so we can combine a nitrile with hydrogen gas under either a platinum or a nickel catalyst, so any inert metal catalyst, in order to create an amine. And so this would just be simply removing the nitrogen group from the end of the, removing a part of the nitrogen group, so some of the bonds from the nitrogen group, and adding in the hydrogen atoms to make it into the amine molecule. We can also do a reduction of alkenes, so this being very similar to our substitution reaction before, where we add hydrogen gas under a platinum or nickel catalyst in order to form an alkane. So that being, for example, forming ethane from ethene. We can also undergo an elimination reaction to form alkenes. So this is like reversing our addition reaction. So we can start off with a haloalkane, and we can use potassium hydroxide in alcohol. And so by adding the haloalkanes such as bromoethane to potassium hydroxide in alcohol, we can form ethene by removing the halogen group from there and breaking the single bond, forming a double bond instead. And so that forms our byproducts of KBr, so potassium bromide, and some hydrogen atoms. The next one we can look at is an oxidation of primary alcohols to make aldehydes or carboxylic acids. So this is a two-step oxidation reaction, and this one occurs only with primary alcohols. So there is a separate reaction with secondary alcohols. So for example, if we take a primary alcohol such as ethanol, we can oxidize it using acidified potassium dichromate or dichromate ions, and this results in the formation of an aldehyde. So in this case, ethanal. And so we can either take the ethanal, or whatever aldehyde it is, out of the reaction at this specific point in time, or we can continue to oxidize it under the same conditions but at higher concentrations of dichromate ions in order to form ethanoic acid or whatever carboxylic acid it has formed. And so in that case, you can then either form an aldehyde or a carboxylic acid. Our next one is the oxidation of secondary alcohols to make ketones. So if we look at this one here, we've got propan-2-ol, and so this is a secondary alcohol. And so secondary alcohols can only undergo a one-step oxidation process. So we have the exact same reaction conditions, so dichromate ions acidified. However, this will form a ketone, so being propanone in this case. So in the acidification, in the acidified potassium dichromate oxidation process, this is only a one-step process for a secondary alcohol, resulting in the production of a ketone. And so we don't have one for the tertiary alcohols because they can't be oxidized. Now finally, we want to look at the complete combustion of alkenes, alcohols, and alkanes. So basically this is just a recap on basically grade 9, grade 10, grade 11 content, but it's always important to just have a recap of this. So we can take a hydrocarbon and we can combine it with oxygen. And so when you see a reaction where the only products are carbon dioxide and water, and one of the reactants is oxygen, you always know that it's going to be a combustion reaction. And so these are pretty common with any molecules which just are made up of carbon and hydrogen, so any hydrocarbon molecules. And so that's why these are related to our organic reactions. So this is taken directly from the syllabus, and this is basically a summary of all of the organic reactions. I would recommend drawing this out, making your own version of this in order to show a summary of how you of all these different reactions, and in order to help you memorize these, because you won't have a copy of this for the exam. So another thing we can do is we can use these organic reactions to help identify solutions. So in order to identify the difference between an alkane or an alkene, we can use bromine water. And so this is because we know that the reaction of an alkane with bromine gas requires UV light, whilst the reaction of an alkene with bromine gas does not require any catalysts. And so we can put the samples of bromine water with our two samples of either the alkane or alkene, so our unknown solutions, in a dark place. And so if the color changes, we'll know that there is whether it's an alkane or an alkene, and then we can put it into sunlight, and if the color is lost, that can also show whether the reaction required UV light or whether the reaction did not require UV light. The next thing we can also do is we can use our primary, secondary, and tertiary alcohol oxidation to determine which type of alcohol we have. So if we have 3 unknown alcohols, we can use potassium dichromate or potassium manganate. And so they each have different colors when they change oxidation states. So you can put the unknown solution into a tube with the alcohol and with the potassium dichromate. And if there's no color change, we'll know it's a tertiary alcohol because tertiary alcohols can't oxidize. If it changes color twice, we'll know it's a primary alcohol because primary alcohols oxidize twice. And if it can only be oxidized once, we'll know that it's a secondary alcohol because secondary alcohols can only be oxidized once.